The three of you on Zoom, Van, Alex, and Caden, are you all doing well? Cool. Awesome. Thanks for answering that, Caden. Okay. Well, again, happy Friday. And we have a long weekend. We don't have class on Monday, so we only get to hang out with each other twice next week. But what I will say is enjoy your day off on Monday because it's the last day off that we have for 2 months. Okay, I don't mean to like burst any bubbles here, but that's the hardest part of fall semester is making it from Labor Day until Election Day or Veterans Day, depending upon what our next day off is. It's kind of a long haul, but once we get there, then we're almost done. All right. Well, does anybody have any questions over anything that I've talked about thus far? Yes.
Doing the one-to-one from the horizontal line to the vertical line.
Yeah.
I don't know if I wrote something down and started doing this on the line. There were 3 graphs that you drew. In any of those, I guess when I looked at them, I was like,
Here, let me. Ooh. So the 3 graphs that I drew when I was talking about one-to-one function, I believe, or maybe I drew, well, I'm just going to draw a few graphs. Like this.
Started right. I thought it started right for the next.
Thank you for asking. I think you're awesome. No, I'm so serious. So I'm just going to draw a bunch of different friends here. Okay. So when we're looking at this, again, thank you for asking. Anything that's ever unclear, please don't not ask. In other words, do ask. Double negative positive. Okay, so first thing is, which one of these 6 graphs, there's more than one, are functions? Okay, by definition, you have a function if each x value goes to exactly 1 y value. So to determine a function, what you do is the vertical line test. Okay. In other words, any vertical line drawn, if it passes through at most one place, you got a function. Is this a function? Yeah. You with me here? Okay. How about this one? Is this a function? Yep. Is this a function? Yep, it just passes through one place. How about this one? No, circles are not functions, but they are beautiful things. How about this one? Is this a function? I claim it is because any vertical line I draw is only going to pass through the graph at one place. Is this a function? No, see, it fails the vertical line test. So these 4 graphs are functions. Now, let's kind of hone in and go a little bit deeper. Which ones of these 4 graphs are actually one-to-one functions? I'm going to see if there's a different color that I can have here. Cool. Which of these are one-to-one functions? Remember, one-to-one functions mean that each output, each y value is only gotten to by one X value. In other words, that's the horizontal line test. And, you know, just to relate it to other ways of thinking of it, not so something is not a function if X isn't monogamous, if you will, right? Because this X value has more than one partner. Okay, just to relate it to other aspects of life. In order to be one-to-one, Y's need to be monogamous too. In other words, I have, like, for example, this Y value here, but notice it's got 3 partners. It's not allowed to. So this is a function, but it's not one-to-one. Because each Y value has more than, or there are Y values that have more than one X values that bring you there. Is this one-to-one? Well, does this pass my horizontal line test? Yes. So this is a one-to-one function. Is this one-to-one? This is going toward the x-axis. I claim this is also a one-to-one function. This is actually an exponential function. We'll get there much later in the semester. Okay. Again, it passes my vertical line test and my horizontal line test. Finally, is this a one-to-one function? No, because it doesn't pass my horizontal line test. I have this Y value and more than one X value brought me there. So this is a function, but it's not one-to-one. Does that clarify? No, thank you, really. What a great way to start the class with a question. Hey, y'all, I'm not ever going to ask you to come out of your comfort zone, but it's awesome when people talk. If I'm the only one talking, life can get kind of. All right, so there's a little bit more that I want to talk about in this first section. And this stuff is notational. Again, my hope is that this is all somewhat review. Maybe the one-to-one might be a new idea. That's totally fine. I reinforce things as we go on throughout the semester. So I never just explain things once. I bring them up as needed. But what I'm trying to do is, you know, kind of get your math brains back in gear after a summer where you probably weren't doing math on a daily basis. Unless you were me. Okay. So last but not least, you might remember that we were talking about different ways that we can display functions. So we saw table, great way. We saw graphs, great way. We had verbal description, another great way to talk about functions. But the last one is one that we use a ton. And not that we don't use the other ones, especially the graphs, but this last one is using function notation or formulas. Okay, and I just want to be sure that you're all at least somewhat familiar with this function notation and formulas. Okay, so you may or may not recall, but to indicate that Y is a function of X, we write Y equals F of X. So Y and F of X are equivalent. They're both my outputs. This is my input. So when you think of these as ordered pairs, you could think of it as your X value and your Y value. And equivalently, you could think of it as your X value and your function value. You with me here? Okay. So If I'm talking about, for example, the line y equals 2x plus 3, the way that I would write that in function notation is I would say it's a function. You can call functions any letter you want. We tend to use F, G, and H because we're just not very original people, and F for function, okay? The X tells us the variable that we're using. This is essentially the rule of the machine, right? It's taking any input, and to get the output, you take it times 2 plus 3. I just made up this function off the top of my head. There's nothing very interesting about it. Now you might ask, why in the heck would we use this notation? Because it turns out that this is really convenient notation, okay? Like if I want to know what is my function value at 1, well, notice on my left side, I replaced X with 1. So I'm going to do the same darn thing on my right side. And you all agree I get 5? So I have the ordered pair 1, 5. Okay. If I want to find my function value at -7, can I do that? Yeah. Everywhere where I see an X in my function F, I'm going to plug in -7. And what comes out? Not a rhetorical question. -11. Okay. What if I want to do this? What if I want to find F of X plus 1? Now, everywhere where I see an X in my function F, what am I going to plug in for X? X plus 1. So 2x plus 1 plus 3. Am I simplified here? No, I need to clean it up a little bit. Are there questions how I got from here to here? If there are, just yell out. No such thing as like raising your hand. So what can I do to clean this up a little bit? Can distribute. I get 2x plus 2 plus 3. So what's my final answer here? 2x plus 5. Are there questions on this? Okay. Same function. What if I want to find f of 1 over z? Now, it's not unreasonable to be like, why in the heck would you want to find that? Why not? Okay. Now, what would we do? Everywhere where we see an x in our function f, what am I going to plug in? 1 over z. So 2, 1 over z, plus 3. 1 second. There we go. So do you agree the best I can do is 2 over z plus 3? Not very exciting. You'll notice I always cross my z's. That's how you can tell the difference between my 2's and my z's. One more. What if I want to find f of x plus h? And if you're like, Lauren, why in the heck would I care about doing that? That seems so ridiculous. Calculus, you have to compute things like this a lot, okay? When you start doing the limit definition of the derivative, this is something that you're going to have to play with. Okay, so this is not just like math for no reason. I promise you. Okay. So what does this look like now? Now, everywhere where I see an x in my function f, what am I going to plug in? X plus h. So y'all agree I get 2x plus 2h plus 3? Awesome. All right. Now, what I want us to do is let's take this function. How about 5x minus 11? And I want us to do two things with this function. One thing I want us to do is solve f of 3, or find f of 3. And the other one is find the value of x where f of x is equal to 3. Now I'm doing this example because there's an important distinction to make. Okay, in this first one, notice that I'm given that 3 is my input and I want to find my output. Notice in the second case, I'm given my output and I want to find the input that brought me there. In other words, in this first case, I'm given my x value. I want to find my function value. In the second case, I'm given my function value. I want to find my input. Do you all see the difference between the two of these? Okay. You ready? What a thrill. How do we find f of 3? What do I do? I put 3 wherever I see an x. And what comes out? 4. Yay. Might as well find thrills where you can. Questions here? If anyone on Zoom has a question, please, please, please ask. How would I solve this second one? You got it. Notice I'm being told that my function is equal to 3. Isn't my function here this? So what I do is I take my function and I set it equal to 3. And now what I get to do is solve. And you are exactly right. The first thing that I would do is you isolate your x terms. So you would add 11 to both sides. So I get 5x equals 14. And how do you undo multiplying by 5? Divide by 5. So I would say x is 14/5. If you want to write it as a decimal, fine. If you want to write it as a mixed number, fine. I'm an improper fraction type of person. All right. Y'all cool this far? Okay. So the last thing that I want to cover in this first section are some of our toolkit functions. These are not functions that you have to like memorize and make note cards for. However, these are functions that I want you to be familiar with and kind of get the feel for, because these are going to be the building blocks from which you can grow. Okay? None of this is a memorization exercise. It's just familiarity. And these are some really common functions that I want you to have a handle on. Okay? So the first one is our constant function. And we'll classify these as the course moves on. And that's just where your function is equal to some number. That's a constant. So for example, f of x equals 7, or we can think of it as y equals 7. Does anyone have an idea of what this function looks like in terms of a picture? You got it. Notice my function value, in other words, my y value does not change. It's always 7. It's a horizontal line. Right? Isn't my function value constantly 7 here? The next friend of ours is our identity function. That says that f of x is equal to x, or we could say y is equal to x. Now, if you're unsure about what this graph looks like, never hesitate to go back to the start and make a little t-table. All this says is, if I plug in x equals 0, what's my y value? 0. Whatever x is, so is y. If I plug in x equals 1, what is my y value? 1, etc. And the way this graph looks is it's a diagonal line through our origin. We're going to see that this is a line with a slope equal to 1 and a y-intercept equal to 0, but we're not going to use that terminology quite yet. If this is review, awesome. If it's not review, awesome. I'm glad we're going through it. Okay, we all need to walk together through this. All right. Another function. Absolute value function. Okay, that's written this way. The absolute value of x. This isn't going to be a really big deal function in this class, but it's a handy toolkit function to have. Do you all remember what the absolute value of a number is? It's the distance, so it's always positive, from that number to 0 on the number line. So for example, the absolute value of 2, well, how far is 2 from 0 on the number line? It's 2. What's the absolute value of -2? Well, how far away, how many places do I have to jump on my number line to get from -2 to 0? 2. Okay, so if you want to make a little XY table, okay, well, how far is 0 from 0? 0. How about what's the absolute value of 1? 1. It's the absolute value of -1. 1. If you plot this graph, you're going to get this V shape. There's a lot of cool properties about your absolute value function that we're going to talk about when we get into more terminology. This is what we call an even function. All right, now we get to some power functions. Oh yeah. So, for example, f of x equals x squared. Again, if we're not sure what that looks like, we can make a little t-table and plug in values. If I plug in x equals 0, what is 0 squared? 0. What if I plug in 1? What comes out? What if I plug in -1? 1. Good. And do you all agree that whether I plug in positive or -2, I'm still going to get 4 to come out? This graph is in the shape of what we call a parabola. In chapter 3, we're going to be doing a lot of studying of our parabolas. This is another even function. What about, and stop me if you have a question, please. F of x equals x cubed. This is our cubic function. Well, if we're not sure what it looks like, what if I plug in 0? What's going to come out? 0. What if I plug in 1? What if I plug in -1? Get -1. Okay. What if I plug in 2? What's going to come out? 8. Any questions? And what if I plug in -2? What's -2 to the third power? -8. Kiki, you good? Cool. Well, if I plot these, I think I showed you this graph before. This is that John Travolta graph. Ding. This is an odd function. Notice this is increasing everywhere. That's cool. Notice this is decreasing and then increasing. All right, 2 more. Next one is our square root function. We can think of this, and I'm just throwing this in so that you don't forget about your exponents. Whenever you take the square root, it's the same as raising something to the 1/2 power. Kind of wanting to throw this stuff back at you. Okay, let's see what this one looks like, because we're going to be playing with our square root function a fair amount. If I plug in x equals 0, what comes out? Square root of 0, 0. What if I plug in 1? What's the square root of 1? 1. I'm going to be very particular. I'm going to go to my next perfect square. What's the square root of 4? 2. My next, what's the square root of 9? 3. Well, if 4 was nice, how about the square root of -4? Can I take the square root of a negative number? No, there's no real number such that when you multiply it by itself, you're going to get a negative, right? Because a positive times a positive is positive, and a negative times a negative is positive. So no. We're going to be talking about things like domain a lot. We have domain issues here. You can't take the square root of a negative number when you're dealing with real numbers. I'm not a bumper sticker type of person because my philosophy is it's no one's business what I think about anything. But I've always wanted to have a bumper sticker that says I break for imaginary numbers, just because then I would be totally labeled as a dork, right? So if you want to graph this, well, 0, 0, 1, 1, 2, 3, 4, 2, you'll see that it grows slightly, but slowly. And I will also just add to tie in class from Wednesday that this graph is increasing everywhere from 0 to infinity. Thumbs up so far? Is it hard to be in a math class at 2 o'clock in the afternoon? It's kind of like nap time, isn't it? All the time is nap time. All right. We are going to dive really deeply in chapter 3 with our reciprocal functions. Okay. A reciprocal function has so many totally cool properties to it. We're gonna dive in with all of the terminology later. Okay, but I want to plant some seeds right now because this is a real cutie. Okay, you're gonna see that cute is a very common adjective for math. Okay, so some things about this function. First off, if I wanted to write this similarly with exponents, do you agree that's x to the -1 power? If I wanted to bring it up to my numerator, I'm only saying that because I don't want you to forget about properties of exponents. It's my way of like planting the seed. Okay. Now there's some really wild things right from the get-go. Can I ask you a question other than the one I'm asking you? Can this ever be equal to 0? No. Good job. Remember, a fraction can only be 0 if your numerator is 0. Okay. So one thing that I want to say is if we wanted to try to graph this guy, we can't plug in x equals 0. Remember, it's illegal to divide by 0. The math cops will come and take you away. Okay, so do not plug in 0. Do you all know why division by 0 is illegal or undefined? Do you want to know? If you don't have to see it, but do you want me to show you? Okay. What's 15 divided by 3? 5. Why? Since 3 times 5 is 15. Okay. 24 divided by 4 is what? 6. Why? Since 4 times 6 gives you 24. Division is just the inverse operation of multiplication. What's 0 divided by 7? 0. Why? Since 7 times 0 is 0. What is 5 divided by 0? Well, it would be equal to some number so that 0 times that number gives me 5. Does any such number exist? No. That's why it's illegal to divide by 0. You're always told these things, but you're never shown why. And to me, the beauty of math is why. All right, so can't plug in 0. Let's try something else. What if I want to plug in 1? What is my function value here? Well, f of 1 is 1 over 1, which is 1. What if I want to plug in the number 2? What is my function value at 2? It's 1/2. Right? I'm just plugging it in for x. What if I want to plug in 1,000? It's 1 over 1,000. So do you see as these numbers are getting really, really big, this is getting really, really small? Okay. I want to keep playing and then we'll graph. What if I want to know what is my function value of 1/2? Well, what is f of 1/2? Isn't that 1 over 1/2? Right? You're plugging in x equals 1/2. And when you divide by a fraction, you multiply by the reciprocal. What do we get here? 2. Are there questions how I did that? If you have a question, okay. You have a question?
Yeah, I don't know.
Okay, so if f of x is 1 over x, if I want to find f of 1/2, do you agree I plug 1/2 in for x?
Right.
Cool. Do you agree what I have written on my right-hand side essentially is 1 divided by 1/2?
Yeah.
And do you agree when you divide by a fraction, you multiply by the reciprocal?
Right.
And 1 times 2 over 1 is 2. Thank you. You are awesome because you asked. Okay. What if I plug in 1 over 1,000? Well, now I have 1 over 1,000. And what's going to come out here? It's going to be 1,000. This is why it's called a reciprocal function, because notice whatever you plug in, you get the multiplicative inverse or the reciprocal out. So what does this graph look like? Well, we have 1, 1. When I plug in 2, I get 1/2. When I plug in 1,000, I'm like really darn close to 0. So we draw our graph like that. Notice this is never actually equal to 0, but it approaches 0. We call that an asymptote. Now notice when I plugged in x equals 1/2, I'm up at 2. When I plug in 1/1000th, I'm way the heck up here. So notice as we're plugging in values closer and closer to 0, my graph is shooting up. Okay, we call that a vertical asymptote. And what you'll see is the exact same thing follows with negatives. If you plug in -1, you're going to get 1 over -1, which is -1. If you plug in -1/2, you're going to get out -2. This function has so many cool properties. We're going to really be delving into it when we get into chapter 3. Are there questions here? All right, what I want to do. I don't want to do that. Let me do something. I'm going to exit full screen because I want to get somewhere. Okay. All right. So what I want to say is this is the general overview of this particular section. Actually, I'm going to exit this really quick. I want to go into something else first. Oy. This is the Zoom problem. All right. There we go. So here is the first section of the book. Okay. They talk about what is a function. They talk about the verbal descriptions. Notice they have the try it now. Those are always really good to practice. This is the function notation that we went through. And then they go through tables and evaluating functions. So for example, find g of 3 and solve g of n equals 6. Okay. And then there's the graphs for the horizontal and vertical line tests. And finally, you will see at the end here, they have these basic toolkit functions. Okay, we didn't do the cube root. We just don't even go there. It's cute, but it's not necessary. Okay. So here are your basic toolkit functions. This is in your book. And they're always at your access, okay? But I wanted to show you how we could go back to the quote unquote basics by making that little XY table, and we could get there without having to memorize a single thing, okay? So those are the important topics in this section. I urge you all, even though people tend not to like to read a math book, that you do read the math book and look through the examples. I think that this is a really good book and that the author takes some really good time and works through a bunch of different examples. What I'm going to do is I am going to open up our first homework assignment, okay? And I want you all to work on the homework, I will set the due date right now in front of our faces before we leave class, okay? And I will once again show you exactly how to get here, okay? I promise. But what I want to ask you is, well, what I want you to do, preferably by class on Wednesday, okay? Technically, here, I'm going to actually go to this assignment. Technically, this is not due until a week from the day that we finish the section. The best thing you can do is work on it now. So what I'm doing right now is I'm setting your due date to be a week from today. So it is due, and today is September 2nd, so it's due on the 9th. It's due on the 9th by midnight. And I just like to set these things right in front of your face so that you know exactly what's going on. Now, just so that everybody knows, once you get into the course, what this looks like. Here's your Math 121 course. How do you find your homework? Okay, well, we're in chapter 1. Click on it. We're in section 1.1. This is probably going to be up here. It's going to look like this. We're doing 1.1. Click on it. Oops. And then you can go down, see your new due date. You can click on this and you can start your homework. Now, couple things about your homework. Number one, you don't have to hit submit at the end. Okay, that's the biggest question. Like in Pearson, My Math Lab, and some of these others programs, you have to hit submit. You don't have to hit submit here. Okay, you can walk away from this and come back to it. You don't have to do it all in one sitting. But let's go through a couple of examples. We have 6 minutes just so that we're just starting these together. Now, your questions are going to look a bit different than my questions, okay? The vibe is the same. The numbers and maybe the stupid little story is slightly different, okay? Now, remember a couple things that I pointed out on day 1. If you need a video explanation, you can click on that. If you try it multiple times and you're not getting it right, or if you try it and you think you're right and that the program's got a bug in it, message instructor comes to me, okay? So take advantage of these resources. One of the things that you're gonna see in this class is a lot of what we do is interpret. We're not a cookbook class like compute these 50 problems that have no rhyme or reason. Okay, we do this math because it models the real world. So it's really important to be able to put things in the context of that. So looking at this first one, the amount of garbage produced by a city with the population P is given by this function, okay? And one would assume that the larger the population, the more garbage produced. Not necessarily. G is measured in tons per week and P is measured in thousands. So what they tell us here is that the town of Tola has a population of 25,000. Is this 25,000 my P value or my G value? It's P, it's the population. And it's 9 tons of garbage. So which one of these 3 expressions does this correctly? Is 9 my input or is 25 my input? 25 is my input. So what we would do is we would click this and then submit. Hooray! Now, if you didn't get it right, you could try again. If you keep trying and you keep getting it wrong, that's when you want to message me, because there's no point in, spinning your wheels and wasting your time if you're not getting it right. Let me help you. But after you've gone through all the tries with one, you can click on get a similar question. In other words, you pretty much have unlimited attempts to do every single problem. Okay, so now I'll go to my next question. Here, what we want to do is identify which of these graphs represent y as a function of x. How can you tell with a graph whether or not you have a function? Vertical line test. So we can then go through and click on which ones of these satisfy the vertical line test. You with me there? Okay. Question 3. This is a cute one. Here, we want to know which one of these tables represents y as a function of x. How do you know if you have y as a function of x? Doesn't that mean that each x value goes to exactly one y value? So let's look at our first table. 3 is going to 5. Is it going anywhere else? No. 10 is going to 7. Is it going anywhere else? And finally, 13 is going to 7. Is it going anywhere else? No. So I would say this is a function. It's not 1-to-1 because notice we have a y value that's hit by more than one x value. Is this second one a function? Well, is 3 going only to one place? Is 10 going only to one place? And is 13 going to only one place? I would say yes, this is also a function. How about this third one? Is this one a function? Okay, I see some people shaking their heads. The reason why this is not a function is 10 is going to more than one value. And this is another similar question. Notice this one's asking the 1-to-1 business. So not only does each x value only go to one y value, but each y value is only hit by one x value. So I would venture to say that in my particular numbers, this is the only one that's a 1-to-1 function. This one is a function, but it's not 1-to-1 because y has 2 x values. And this is not a function because this x value goes to more than one y value. Okay, what I want you to do, please, this again is not due until next week on Friday, but if you can make some time and work on it between now and Wednesday, I'm going to start out class on Wednesday by asking if anybody has any questions, and I'm happy to work through any and all of these. Okay? Is this okay so far? Is the pace okay?
I think so.
Okay. I know people tend not to love their math classes and, feel anxious about their math classes. So, if you have concerns about the pacing about any of this, let me know. I hope you all have a super duper fantastic weekend.
You as well.
I will try my hardest.
All right.
Everybody on Zoom, have an awesome weekend. Thanks for coming.